So the first part ended with this guy being the key to how these ladder operators are working, but let's look at that in a little bit more detail just to make sure it's clear what's going on. So as you can see here, I have 4 terms here. Let's go ahead and just rewrite that a little bit more clearly. So I have negative h bar squared and then the second derivative with respect to space. And then I have this mass squared plus omega squared times x squared. But then I have these 2 terms out here. H bar m, the derivative with respect to x of x times our test function, plus mass times omega, oh, there's an omega there, times h bar, so same constants out in front, but now I have x, which does not have the derivative taken on it, times the derivative, which will be applied to our test function. I said these 2 terms, that is the key to why these don't commute. So why is that? Well, that has to do with the product rule. So let's take a look at our product rule. This says that if I want to take the derivative of f times g, and I take the derivative of that, so just that little prime mark, apostrophe mark is a signal that I want to take the derivative of that. So I can't simply just take the derivative of x and multiply it by the derivative of g. So I can't just take d dx of x, go ahead and perform that operation, and then have that times the derivative of f of x. That doesn't work. I have to consider the derivative of them both together. So if I have a function that looks like this and a function that looks like this, the 2 of those multiplied together look like this. It's a cubed. That is different. That has a different derivative than this derivative and this derivative. So what I have to do is use the product rule. So that says that my derivative of f times my function g plus my function f times my derivative of g. So that means that if I do d dx of x times f, then what I get is the derivative of x. We'll call it f of x because I called it f of x before. So what I get is, put that in parentheses, what I get is d dx of x times f of x. So now my derivative is only operating on x, it is not operating on f of x. And then I have plus x multiplied by the derivative taken of f of x. Or as he wrote it in the textbook, he wrote it like this, where you have d dx of x times f is now, and that's just a 1, right? So d dx of x, the derivative of x, well, shouldn't use f, we'll call it g. And g of x just equals x. My slope is just a 1. So what I have is x times my derivative of f plus just f. That's the way he wrote it in the book here, which he wrote as, just a little aside, even though You know, if it wasn't obvious to you, I don't think you're alone there. Okay, so let's go ahead and clean that up then. Taking that into account, right? So now taking this result into account, what I get is I can replace this up here. Is that the one? Yep. I can replace that one with this. And then what I get is a cancellation of those two terms. So I'm going to try to write it out for you. So I have a plus a minus acting on f of x. And then I get 1 over 2m. I get all this junk out in front that I already had. Which I don't really care about. But now this one, I get h bar m omega times x dx plus, it's supposed to be another negative h bar m omega times, well, just h bar m omega because I already factored out my f of x. And then we have plus m omega h bar x dx. And then that's all acting on this guy. So this one here and this one here cancel out. So what I get is 1 over 2m negative h bar squared ddx squared plus m omega squared x squared minus h bar m omega. And I can throw out my test function because I'm done with it now. That's what we have here. Yay! And then I can play around with those a little bit here. Wrap those up into squares. And then what I get out in front, what I get out from it all, if I factor out that 1 over 2m, what I'm going to get out of that is I'm going to get a 1/2 h bar omega. So I had h bar m omega. If I factor out 1 over 2m, that would be, or factor out the 1m, 1 over 2m, we get that h bar omega there. That guy. Okay, so this is what we get out of it when we factor it all together. Hopefully that's not too hard to see how that all works. It's just taking the squares of those terms. And this comes out. I gave it some thought and realized it's probably not that obvious. So I'm going to go ahead and do it explicitly. That took like 5 minutes for me to decide that. Okay. So let me go ahead and show how that happens. So I have A plus, and I'll write that as an operator, and my A minus operator. And actually, let me go ahead and erase that. Let's go back a step. Okay. So I write those out explicitly. Now so I have A plus A minus. I get 1 over 2m. I get that term in front. I get this guy coming down. So h bar times the second derivative. I get this guy coming down. And then those guys canceled out because I applied my product rule, and then this guy comes down. Now you may notice I have a negative sign here. If you got a negative sign, don't just pretend like it's magic. You'll see why in a second. Now, I have A plus A minus 1 over 2m. Let's go ahead and wrap this up into squares. So I have h bar over I d dx, gonna square that. Now I have my m omega x, that's gonna be squared. This is not convenient to take a square, so I'm just gonna keep it that way. Now I could multiply through my 1 over 2m, but I don't really want to for the first two, so I want to keep it out for these first two, because that's how we defined our operator to begin with, right? So I'm going to keep it the same for these first two, but then if I multiply it through, or I distribute it in here, I get a negative 1/2, right? So this is 1 over 2m times this, and then I get an h bar, and then my mass is canceled out, times omega. This is my A plus operator multiplied by my A minus operator. And my A plus A minus operators look like this. So my A plus operator is this guy plus this term, and the minus one is minus that term. So you see I get this minus 1/2 h bar omega. Here you will notice that he has a plus sign. That's because he did A minus times A plus. I did A plus times A minus. That's the difference in sign. So if we do the whole process again, what we would find is the exact same result, just that sign is going to change, because in particular, you know, when we're foiling this out, that has a I cancels out the I, that one's negative. That's negative, but then it's times I squared, so it's positive. If these are swapped around, we get one of those signs is different. And then this one we have I minus I divided by I cancels out, we get a negative. Same idea, we get negative times -1. If these signs are swapped, we get a different sign, because that's how operators work. So that term, when we take it out with the product rule, just yields us a different sign. Okay, so it's not perfect, it doesn't commute perfectly. We get an extra 1/2 h bar omega, but we can conveniently just pull that onto the other side. Let's just put it over here, And what we get is that our A minus operator times our A plus operator minus 1/2 h bar omega times psi would equal the energy times psi. Right? So this is the whole stuff that was in front of, psi to make that work. So our Schrodinger looks like this. 1/2 2m plus m times omega x squared, all that times psi equals energy psi. But I could go ahead and say that my A plus operator times my A minus operator plus 1/2 h bar omega equals this whole guy. So I can just go ahead and replace that into the Schrodinger equation instead. So what I get is, in my case, because I did my raising operator times my lowering operator plus 1/2 h bar omega acting on psi equals the energy times psi. So we can just replace it in here. All I did was just the operators in the opposite order. And I get a positive sign there. Plus the 1/2 h bar omega. So, kind of a spoiler, as he noted here, the ordering of the factors A plus and A minus is important because it gives you a difference of these signs. If we look at the commutation relationship between them, if I just did A minus times A plus like he did, you get that plus sign minus the one that I did where you get that minus sign. What you'll notice is you will get a factor of h bar omega. So these two operators multiplied together do not commute. They have a factor of h bar omega that causes them to not commute. There's the result that I got.